All right, welcome everybody to our special session on understanding the underlying technology behind generative AI. We're going to be taking a look at transformers and getting a better sense of how transformers work. And we're going to be doing this in using two different sources. One is going to be a paper that I very much like. It's called Formal Algorithms for Transformers. And what it gives you is formal pseudocode. So you can take a look at transformers. And what you're going to see, it's a very compact, very concise way, very precise way of describing exactly what's happening algorithmically with the transformers. And then the other source that we're going to be using is a book. And it's hard to believe it was only published in May of 2022 because it seems like forever now, by some of the folks who were the founders of Hugging Face, which many of you now know is a fantastic site for all things transformers. Their book is much more, it's visual, and then it also goes heavy into the coding. What we're going to be doing today is sort of marrying the two. So nice thing about their approach with understanding transformers and applications of natural language processing is it's very coder friendly. They describe things by giving you code, which is really nice for people who've been coding a lot, but not so useful for people that aren't coding a great deal. And even if you code a great deal, it still obscures what's happening with the transformers. It's hard to understand and get a good feel for what's happening in transformers just by looking at code, frankly. And the other side is Formal Algorithms for Transformers. Great paper, also pretty dense. So we're going to be trying to take a look at both and try to understand both. So the goal by the end of today is for you to have a better understanding of exactly what's happening underneath the hood. This doesn't mean that you will understand everything by the end of this 2 hours, but you'll have the understanding of how these things fit together. I also would like to give you tools so you can dive more deeply into especially the formal algorithms for transformers. I will point out that a great way to get personalized explanations of what's happening, and especially in papers like formal algorithms that can be dense in parts, is GPT-4 itself. So yes, wonderfully meta. You are using a transformer to help explain to you a paper about transformers, but actually it works really quite well. Something else that I'll mention is that now, if you have a paid account with OpenAI, and this is going to be the Chat Plus, now you do have access. You'll have access to GPT-4, plus you'll have access to plugins. And one of the plugins you're going to want to keep in mind, especially when you're doing anything mathematical or anything where you want to have, scientific information, or, you want to have the facts, you'll want to use the Wolfram Alpha plugin. And we'll do this at the very end. So we'll do our session here, and then during the office hours, I'll show you how to actually enable those. All right, before we dive in, any questions that anyone has? Raymond. Did you have a question, Raymond?
Yes, I posted it in chat. I was just asking if there was a resource for long context use.
Okay, not really. So long context use now means, by the way, long context used to mean 16,000 tokens or maybe even 30,000 tokens. But now long context means 100,000 tokens as of 2 weeks ago, when Claude Instant 100K was released. Not really, there are papers on it, but ask me during office hours and we'll dive more into what resources there are. Any other questions? All right, then let's go ahead and dive in. So what you have on the screen here, and apologies for the crowded screen, going to be covering a lot here, is over here to the left, I just have the paper open. I'm sorry, over to the right. Over here, I just have a presentation, a lot of which are going to be illustrations from the NLP book by Tunstall, Wera, and Wolf. I'm going to keep this in this display just so you can see the context of exactly where we are. Can everyone see everything all right? Can you see the words well enough? Okay, fantastic. Then let's go and get started. When transformers were first released, the very first transformer was one that was what's called an encoder-decoder. Now, at the time, of course, it was just called transformer. This is kind of what this was the idea. And the idea here is broadly that you start with text, and then that text immediately gets turned into numbers because deep learning models can only deal with numbers. Those numbers are transformed. They're enriched. The numbers are turned into embeddings in a high dimensional semantic space. So just to begin to wrap your head around what a high dimensional semantic space is, an archetypical example is king, man, queen. So you're in a high dimensional space. This point right here, this one right here, stands for king. So if you look around it, it has all the things. If you actually just take that point in space and you move, and quite literally, it's a vector. So in the case of, I think, the original BERT, it was 768 dimensions, much higher dimensionality now. But if you get anywhere close to it, you're going to have things sort of related to it. King, prince, king, maybe regent, king, it's going to be all the things right around king. So this is a real space, and you can do math with it. So for example, if I were to choose a place, if I were to choose the word for man right here, right? So I have the word for man, and now here's a point in space, it's a vector, which represents man. I can subtract the two. What do you suppose I get if I take king and I subtract man? Where do I end up in the space? What's the word close to where I end up in the space? Any ideas? And you can either unmute if you'd like, or you can put that into chat. Well, yeah, Ryan, you almost queen, except all I did was subtract man, right? So almost monarch, prince, yeah, I think you're right. And maybe even regent, but monarch, I think that's close. So if you subtract one from the other, you end up over here, and here's monarch. Okay, now I'm going to take the word for woman, the embedding, the vector for woman. I'm going to add those two things together, just add them. Now where am I? What is this point? So it's king minus man plus woman. Where am I? Yeah, exactly. Now you're at queen. So the words get turned into numbers, which are turned into into embeddings, which are then you can do math on. So you can literally take the average of two words. You can subtract. You can, this is insane, but that's exactly what a word embedding is. So that's what's happening here. We're taking these words, we're assigning them each a number, but then we're very quickly coming up with embeddings. They're starting embedding. So I'm going to start up, I'm going to take man. All right, I'm going to give it a 5. Man is 5. All right, now I'm going to do embedding. That 5, okay, now I'm going to embed it here. So now it just has its starting place. This is going to be its position. What the encoder stack does is enrich the space. The space starts out very, very simple. The encoder stack moves points around and sort of redefines the space to make it richer. Okay, then you have your final position. The hidden state is simply where things end up. So how do you run this? You could put a word in here, and then you run it all the way through, and then you have the position for the word. You could run multiple words through, and then you have positions of all of those words. So turning words into positions in a high dimensional space. Down here, something similar is happening, but you do something different with it. And in the original one, and we're not going to talk too much about this, is the two are sort of yoked together. This one trained on English, this one trained on German. And there's communication between them that we'll touch on just a little bit as well. So it allows you to do a translation from English to German. Let's dive in a little bit deeper to this. Turns out you don't need to have both these things together. It turns out that you could do just the decoder part, this part up here, the blue part, and it's really useful because what it's doing is you can use it to predict the next word. So this is exactly what generative AI is doing. Generative AI refers to decoder-only transformers. So generative AI, GPT, GPT 3.5, chatbot, GPT-4, Claude, Bing Chat, any of the generative AI models that you'd care to talk about, Bard, they're all decoder transformers. Words come in, they get identified with numbers, you get the embeddings become enriched, and then from that, you predict what the next word is going to be. Michael.
I guess, I can understand the decoding part, but in order to do the decoding, at one point, all the things that you put, for example, as a prompt or whatever, it has to be embedded or encoded somehow, correct?
That's right. And it's encoded, and we're going to see that it's encoded token by token. Remember I said it can't take words, it has to be numbers, right? So you have to start out with numbers. So the trick is you don't identify each word with a number because you have too many of them. So what you do is you do very common words and then you do subwords. This is called tokenization. So this is taking an input text, breaking it down into a sequence of numbers, of integers, which are really just indices, which give you that first starting location of each of those tokens. Ryan.
So you mentioned that words essentially have a position, and I'm curious about the dimensionality of this positioning. So for example, you mentioned like the word king and how you might have regent nearby, etc. But considering the amount of access, the amount of words these things have, I'm trying to just visualize the interaction between the dimensions and how that might interplay with their function as a position with the vector.
Okay, so two different things, just to be clear. So when I say position, I mean position in the space, which is really a point, which is really a vector, right? So that's just a vector. Position within the vector of the words. I said the following. So where's the? I said the. Oh, it's the third position, depending on how you count. Third position. That's a little bit different. That positional encoding of where the words and the tokens appear within the phrase actually just show up here. We'll see that in a moment. You'll see that it right here, it says position embed. This can either be sort of a heavy duty one, or it could be learned, or it can be light. So yes, you are recording at what point in the sequence did this word appear? And we'll talk about that. So two different things. Now, in this hidden state, now I'm talking about where does this token now exist in this high dimensional space? So 768 dimensional space, or maybe several thousand dimensional space. That's the semantic space, and its position is its meaning. Paris.
I had a question about, so if the LLMs don't have encoders, so I'm assuming that these are already, that the encoding is already programmed in it. Is that?
So here's a problem with encoder decoder refers to just how to characterize what the transformers are. They do a lot more than that. Let's go ahead and take a look at this is a decoder transformer. This is an encoder transformer. Notice that they all do their token embeddings. They do the token embeds. They look almost exactly alike, right? So they all are taking the words, turning them into tokens, putting those into an embedding space, putting them into a richer and richer space, and then returning something. But what's happening with the decoder is its job is to predict the next token, the next word. The encoder transformer does exactly the same thing, but its job is to return the hidden states. It's just returning that rich, so each token that you've put in is now in its special place. And then if you want to do anything useful with that, you have to put on another, what's called a machine learning head. So you want to do clustering on it? Great, put a clustering head on it. You want to do classification? Fine, put a classification head on it. But the end product and the deliverable for the encoder is those hidden states. Whereas the endpoint, the deliverable for the decoder transformer is the next token.
So I guess while training, it would be like an encoder model, whereas right now when it's working, it would be a decoder. Is that accurate? Or
could you repeat that one more time?
So like when you're training the models, it would work, I guess, as an encoder. Whereas right now, when we are using the LLMs, it's just working as a decoder. Or I'm just trying to intuitively understand.
Yeah, sure. Encoders and decoders are architectures. So we haven't even really talked about training yet. Everything that we've talked about up to this point, we sort of assume that this is ready for us. And you can think of it in the following way. Words come in, something comes out. With a decoder, words come in, words come out. The predicted next words. In an encoder transformer, words go in and hidden states, which are the positions in this high dimensional space, come out. And what does that look like? That actually looks like, let's say that you put 10 words in here, 10 tokens in here. What you're going to get out of here then is going to be 10, and let's say we're using BERT. It's going to be 10 items. It's going to be 10 items that are 10 vectors that are each 768 dimensional, 768 long. So it's going to be the position of each of those tokens. I am learning. Okay, so what's going to come out? 3 vectors of length 768. And then this long vector, which is going to be real valued, right? So it's going to be, 1.505, 0.15, it's going to be a long vector that represents the meaning of I. Am, that's going to be a next one. It's going to be 768 dimensions, and it's going to be describing the meaning of am as it occurred in this sentence. Learning, same thing. So in the encoder, what comes out and what's the important deliverable is all of those positions, and then you have to do something else with it. And that's called the machine learning head. So you could do all sorts of things. You could do extractive question answering. You could do classification, a number of different tasks that you could do. Adam.
So I get that that the tokens end up as a position in this abstract space,
Right.
embedding space.
Yeah, from between here and all the way here. Yes.
Yeah. So is there a concept of grouping and distance in that space? So, if you have north, south, east, and west, are they going to be close to each other necessarily? And if you add them together, they're going to mean something about directions? Or is it more, are those relationships more implicit and not a feature of the location?
It is a highly meaningful space. So, how good the space is and what it captures is really dependent on what it was trained on. So and where you end up is going to depend not just on what the word is, but what it's supposed to represent, right? So if I say west, well, what does that mean? It means something very different if I said, I live west of here, versus if I say the wild, wild west. In that case, west is 1700s. It is, wild, wild west, and then, oh, horses and 6-shooters, versus the other one is that way, right? And the thing about transformers is, based on the context, it informs where that point needs to be in the space. Simple embeddings don't do that. West gets one location. In the original, when we were originally doing embeddings, 13 years ago, longer now, West had one position because it was the word West. And if you actually meant wild, wild west, well, that's just too bad. Now what happens, it takes the full context, and each word is informed by every other word that's in the context. And that's the critical piece. That's the role of attention. Attention is exactly what tells you how to interpret that word based on the context. So I'll make one other quick comment about how these are also different. The architectures are almost exactly the same, you'll see, but what you do with them can be very different. The training is also a little bit different too. In decoder transformers, usually what the training is you have to guess the missing word. We talked about that at the beginning of the AI summary. You have to guess the missing word, but that missing word is always at the end, right? So you just choose a word at random. You remove words in the context after it. So in decoder transformer, you get all the words up to a certain point. And you have to use all the words up to a certain point. That's what you learn. So it gets good at to figuring out what word comes next. It's called causal language modeling. Have all the words up to a certain point, guess the missing word. So that's what it learns. Encoder transformer, what you tend to have, the training looks like you remove a word, but the transformer gets to see everything before it and gets to see everything after it. So during its training time, it gets the entire context. It's called bidirectional. So encoders and decoder transformers have slightly different architectures, can have very different uses, and have different ways of training. So questions so far. And here, let me give you an overview. This is transformer, the original one, the encoder decoder transformer, things like T5, BART. These are encoder decoder transformers. Decoder transformer, these are the GPT families that we know and love. Encoder only, this is BERT, all of these models. So you tend to see these models being used for things like classification and extractive question answering, and where you come up with a task and you provide additional training on that task. Decoder transformers, all it's doing is producing the next word, which means everything is natural language. It's just producing words, right? So you could train it to know what you mean when you are asking it to do things. So working with these models tends to be purely natural language, prompt engineering. Working with these models involves additional programming. These models, the very useful ones, tend to be much larger because you want them to learn not just the concepts, but you want it to learn instruction following. You want it to learn there's a lot more to learn. So these tend to be huge. These can tend to be smaller because they're doing fewer things. And if you want them to do something very special, you give it a special machine learning head and you train it further. What questions do you have about sort of the family of transformers? And Adam, did you have another question or just?
Yeah, so I had a question related to Audrey's question in the chat. Okay. So if you're working on images, would that be a decoder like Midjourney? Is Midjourney a decoder?
So they are related in that there is a language component, right? So there's a language component to Midjourney, which is really transformer driven. But you also have other things which are called diffusion models. they have in common this idea of this high level sort of semantic space, right? So you can train transformers on things other than text, for example. It's any sequence. So it could be images, could be sounds, could be anything. They're general purpose, powerful learners. And you're just talking about a sequence of symbols, a sequence of information over time. In diffusion models, it learns about the space of images. But that idea, if you take something and then it gets enriched into this semantic space, and then you come back out of that space. So that kind of journey is the same. All right, great. Let's dive into a little bit more what that encoder looks like.
Sorry, Jesse, I just had one more question.
Please.
So does that mean that all of the decoder transformers also have like an encoder attached to it that they're using as like the beginning step, or like the decoder inherently includes both an encoder and decoder aspect to it?
Yep. Encoders. And so remember, encoder, decoder, they're just the names of, frankly, I think they're kind of unfortunately named. And the reason they are named this way is because of the original one, right? So it's like, originally it was like, oh, this is the encoder part, and oh, this is the decoder part. And then people realize, oh my God, you don't need the whole thing. You can have just that, what we originally calling the decoder part, and it can do everything we need it to do. Or you can just take you can take the encoder part. It can do everything we want it to do. So unfortunately, the name stuck. Encoders have everything you need to take words into the tokenization, into the embedding, and then out to something useful. They both have everything they need. But think of encoder transformer. Instead of thinking encoder, think encoder transformer always. Just think encoder transformer. It's just a name. It'd be far better if we maybe had called one, if we called the decoder generative. It'd be so much easier. Decoder transformer is a generative transformer. Does that make sense, Audrey?
Sorry, so it's a generative transformer, but it includes what are thought to be encoder functionalities to it?
Well, let's, I'm going to stay away from that word, so I'm not going to use that word.
I guess
context, it just because I don't want to use the word encoder to describe what's going to be happening next. So the decoder transformer involves all the machinery, which will take your words, assign them numbers, give them initial vector representations, then put them through what's called the decoder stack, further enrich those representations, give you hidden states, which are just the vectors that we talked about before that represent each of the tokens, and then use that information to predict the next token. It's generative.
Okay.
And it can do everything. Using just that decoder network, you can think about it. You could train on, let's say you trained a decoder on English and on French. Great. Then, or English and Spanish, right? Then great. If you put the word water in here, okay, it's going to end up here. Great. And then if, I would like to have some water because I'm, and next word is going to be thirsty, right? Or you could be doing Spanish. You have to say, I have thirst. And I don't remember what the word is, but agua, if you have the sentence which means I am thirsty or I have thirst, said, right? Tango said, right? All right. Tango said, necesito agua. All right. And then that's going to end up in the same space. So it doesn't matter if it's multiple languages. So all the things that we used to think we would need to have the full encoder decoder transformer, we don't. You can do everything you need to with just a transformer, just a decoder transformer, which is a generative transformer, meaning it produces the next word. You can also do dead useful stuff with just an encoder transformer, where it ends up with the embeddings. all part of a family tree of all types of transformers. And you're going to see in just a moment, the architectures are very similar. Other questions? And Audrey, does that answer your question well enough so far? And we're going to dive into that more also.
I think so. I mean, I think I was generally thinking about this like the relationship between a multiplexer and a demultiplexer, but I don't think it's really like that.
Yeah, and you can see how it's unfortunately named, right? I really wish they had not called them encoder transformers and decoder transformers.
Yeah, okay.
Yeah, Adam, and then Jay. Okay, great. Jay.
I was just wondering what happens when we train decoder in two different languages, but for a word from two different languages that shares a similar meaning, but also has a different contextual information to them. How does decoder model actually deal with that?
So, a number of different ways you could do it. You could, one thing, I mean, you could certainly just feed in all of the text and not even say what language you happen to be learning at some point. Matter of fact, a lot of them do that, and they're multilingual. It's just two languages, it's many languages. So if I'm so if I say tango frio, or if I say I am cold, or if I say il fait froid, and Holly, correct me because I know that's just wrong, then it all ends up in the same place. I'm cold. So it can learn all of them all together, and all that it's doing is learning. It's being trained to do the next word prediction, but because they all mean the same thing, they're going to end up in about the same high dimensional location, which means that you can now translate, or it doesn't matter what language that's coming in, the representation is the same. Does it help a little bit, Jay?
Yes, actually it does. Thank you.
You're welcome. Holly.
Yeah, so this is where someone who's not in STEM has a question, is languages don't always have a one-to-one correspondence semantically. So how is it handled? I understand, you've answered the question how syntactically, right, that can work. But what do you do with polysemy, some multiple meanings of the same word that do not compute across languages?
So remember, this is a space, right? So this is not, you're not exactly making a link between the two, right? It's generally where it is, right? Like, I don't know if it's really, does it really mean the same thing when you say I'm cold versus il fait froid? Is there a subtle difference? There might be. And that can be, and if there's enough information to train on, that will be represented in the structure of the space. So it doesn't have to be perfect. It's okay if it's in the neighborhood of. And when you have multiple meanings for a word, depending on the context, remember that encoding takes into account all the other words. You're not just doing a word, you're doing the entire context. So like Wild Wild West versus west of here.
That helps a lot because, I am hot in both languages can have different meanings. And so it's not just looking at subject, verb, adjective.
No.
It's looking at the sentences prior to it to figure out whether you're talking about temperature or it's, out on a date Saturday night.
Right. And, the wild thing is we never explicitly train it on the grammar. It learns it incidentally by being exposed to it. Great questions. Other questions? Then let's dive in a little bit. Let's take a look at the decoder transformer and what this means algorithmically. So, first of all, I've been talking about tokenization. Here is how you specify tokenization in a rigorous manner, but with a sort of a shorthand, a mathematical shorthand. So we identify words and subwords with numbers. So we have a vocabulary of numbers where V is just the number of tokens you have. So V is just the number of tokens that you have. Let's say you could have thousands, you could have hundreds, but usually thousands. A word could be a token, or you might have some unusual words like paymaster. Does paymaster need its own number? No, it probably could be paymaster. 3, it could be 3 tokens. So the tokens are the numbers that are associated with words or subwords. That's the first thing. The other thing is that the way that you get a sentence out of this is you string a whole bunch of those together. So I am cold. All right. So that could be 54, 9,200, 1301. That could be the phrase. It could be if each word was associated with a number and it looks like X. X is going to be defined as going to be one of just a length of tokens up to a certain amount of time. So what is X? X could be a sentence. It could be a paragraph. It could be a full page of text. If you're in text, it could be, if you're in other modalities, it could be other things. But you can think of this as X as being like a whole phrase, a whole context. This right here is, this means that it's an element of all the possible vectors, that V star is the superset of all the possible. This is, this is all things that have been written of a certain length up to, say, 1,000 tokens. Everything that has been written and could be written. That's V star. And so what you're saying here is that this X is going to be somewhere in there. So let's talk about what we're doing with decoding transformer, a D transformer. Maybe that's the way to think about it. D transformers versus E transformers. So we don't get too caught up in the encoder decoder part. So we're going to take our phrase here. We have X in. X in is going to be just some phrase. X is going to be some phrase. X in is going to be all the training data we have. So this could be all of Wikipedia. So each X is a Wikipedia entry. Our job is going to be given some X. We want to guess what the next token is going to be. So the formal way of saying this is to learn an estimate of P hat, the probability distribution of Px. So what we're saying here is we want to figure out not just what the probability, we don't want to really, we're not just guessing the next token, the next word in a context. What we're really doing is we're getting a probability distribution of all the next things that could be. So ships at a distance have every man's wish on blank. So probability of the word being dirt, really low. Does not make sense, right? Probability of the word being deck, not bad. It's pretty high. Probability of the word being board, even higher. So what we find there is that deck and on board both have high probabilities, but on board is a higher probability. So what the decoder transformer does is give you that probability distribution over all the subsequent tokens. So questions, let's let that sink in for a moment. Questions about that? Okay.
So I have a question.
Sure.
Does it actually, these generative models, is it really just word by word by word, or does it take into account, like, I might use some phrase in the future, and because I think I'm headed this way, this is the right word to use?
Think about the training.
It's not doing that.
Right. It's the causal modeling, meaning you get to get everything that came before.
Okay.
So, you know, and frankly, we could spend the rest of, I could make an entire course out of this paragraph right here and this conversation. Because think about everything that means. And we are going to spend some time to unpack all this. That means the only way that you can steer these models is to provide better context. Because it only is using things that came before, and it's always doing it afresh, right?
Right.
Then that means you've got to give good context for it to be able to know where it's going. Okay. So that's where prompt engineering comes from. Prompt engineering is coming up with sufficiently good context, and so it goes in the direction that you want it to go. What are some other ways that you can improve a model and so it goes where you want it to go, so it produces the kinds of things that are useful to you? You notice right here, this is a theta. Any CS people here who have a guess at what theta might be if you looked at the paper a little bit? Langdon, I think you might have a...
If I remember from your class, we talked about theta as just everything the model knows. It's all the estimated parameters.
That's it. So you see what I mean by this being a very concise notation? This one character right here, this p hat sub theta. P hat means that it is the estimate. So this is the estimate of what that probability is. What is the probability of a board being the next one versus deck versus dirt? What are the probabilities? So that's what that p hat is. It's its best estimate. Theta means that the way that you're coming up with that estimate is with a decoder transformer model, a D transformer. Theta is all the weights of the model. It's everything that the model has been trained on and known over time. So what does this prediction of that next token depend on? It depends on certainly on the X that you give it up to that point, the context. Prompt engineering is important. But second, it's everything that the model knows. So one way to improve how well the model does is to train the model more. And everything, and that's everything. That's it. You can train the model more. You can give it better context. Now, I am leaving a little something else out here. All that's happening with all of this right here is it's just predicting the next token, right? But we know that it's actually producing whole sentences in response, right? It turns out that it's awfully useful for the next word prediction to do a little bit more than just the next word. That's called greedy, just doing just the next word. Instead, what's often done is that you generate a phrase. So one way is you generate a phrase until you get to a stopping point where a period would naturally appear. You know, where it says, okay, I'm done. And you predict a number of those. Remember, we add a little bit of noise. It's a little bit of noise, so we don't choose on board. Maybe we choose on deck and see where it goes. Okay, then we do it again. This time we happen to choose on board, and then we see where it goes, see where it goes, and then stop. Those are called beam searches. So it's doing more than just the next. Nothing else is changing, but we're using the model to generate a whole bunch of possible paths, and then we choose a path that we like best. That's based on some optimization. So just know that this is technically exactly what's happening and all that's happening, but then we go a step further when we're actually doing the prediction. We do a little bit, we sort of collect all the information that we have and say, this one's repetitive, so it's not going to be as good. This one is just the same token over and over and over again. Maybe it just starts saying, which we certainly do, but it's not interesting. So we penalize that. So the decoder transformer is always only doing the next token, But then we may take that in an additional algorithm and do a little bit more with it and do a beam search.
Yeah, so I think that's kind of what I was trying to get at before,
Yes.
right? It's that, like, ships at a distance have every man's hopes in the hold or in the wind or on their sails, right? Like there's lots of prepositional phrases you could put on there. It's like once you commit to on, it's like you got to keep going. But that's what you're saying is like you can almost simulate a couple of different reasonable paths and then kind of generate a distribution over this like subset where I've actually generated several different possibilities,
right,
and then choose the best one.
Yeah.
That's kind of, I think, what I was getting at before. So they are doing something like that.
Yeah, but remember that selection is much simpler, right? There is a whole lot going on in here that we're going to be talking about for the last part. A whole lot. Here, it's just like I'm going to penalize, I'm going to penalize repetition. I'm going to penalize anything that just repeats what was in the context. So that's going to count less. So it's not as informed. This is more along the lines of, you're trying to optimize a little bit there. So that's the only caveat, that yes, you're sort of looking ahead to sort of make some decisions, but it's not really deep analysis of it. It's much more surface, if that makes sense. Michael.
I guess you talk about the penalizing, I guess in how the algorithm actually implemented. Is that using some kind of active function, or what? I'm trying to visualize, let's just, for example, how does it penalize, right? Is that hard-coded?
So this is a separate algorithm, and you can have exactly the same. You could have GPT, you could have a GPT-2 and have two totally different heads on them that are doing two different things in terms of how it is predicting or how it is choosing which beam to choose. Know that there are many different ways you can do that, right? So that's not the core part of the transformer. That is something that you're sort of doing with what the transformer gives you. What is the transformer giving you? It's giving you that p hat. It's giving you that probability distribution over all the tokens. It's a tool to generate those probabilities. If you want to do something else with it, you can. And if you remind me, I can point you in the direction of some papers that sort of talk about different optimizations, different algorithms that you may choose to do that. All right, questions about this? Okay, then let's talk about what an encoder, the E transformer, the unfortunately named encoder transformer, the E transformer. So here, given a vocabulary, this is doing classification. I don't know. I think I might skip over that one for right now. Yeah, I'm going to skip over that for right now. Change my mind again. Let's talk about it. So remember I said with the E transformer, the encoder transformer, it comes up with these representations and then you do something useful with it. One useful thing that you could do is do classification. So you might choose to do a simple classification. Is this a positive statement or a negative statement? Or something really complex like which of the 18 styles of negotiation does this sentence represent? I was doing that last week, right? So it could be really complex type of classification. You can use an encoder transformer, an E transformer to do that. What happens? You get a vocabulary and a set of classes. Let's do just positive statement, negative statement first. Two classes, positive or negative. And what you do is you you get a whole bunch that are matched. And then what you do is you try to come up with to learn an estimate of the conditional distribution. Given X, what is its category? So this classification head becomes, hey, given the embeddings of the X that I put in here, what is the associated category that goes with it? straight classification. So what is the end result of this? 0, 1, 0 positive, 1 negative. Or in the case that I was doing last week, 0 through 17. So it's just associating the embeddings. So given the text, create the embeddings, now associate those embeddings with a category. Yes, Holly.
Yeah, so what is it basing the outcome on? Are things that have already been categorized in the data set, and how is that categorized in the data set? So, there's a website, there are websites where somebody said, here are the 18 categories, here are some examples.
So this is, in this case, what you're doing is you first do, so you have this model, which is sort of ready to go, but now you have a classification that you have to train. So you need to have some good examples of, here are like a couple of 100 examples of each of the categories, or fewer. Sometimes you can get with very few. These encodings are terrific. So you can learn on very little data. It's called supervised fine tuning. And then absolutely, then it sort of learns how to generalize from there. Excellent. How does it do this? Well, one thing that that we want to let's think about what's happening with attention. We talked about this before at the very beginning of the AI summer. What's quite literally happening is that the vectors for the words get blended together. So let's take a look at time flies like an arrow versus fruit flies like a banana. Now, all of these words are operating very differently, right? So how do you put the word flies in two different locations in the space where this flies means like multiples of the annoying things that are in your house versus this flies, which means is a verb. It means something more like soaring. Well, a way to move towards that is you let the other words in the context inform your interpretation of each individual word. So let's take a look at flies. Time flies like an arrow. So what is flies going to be informed by? Well, flies is a verb, and it means something like soars, right? In order to get that, the way that you get that is you get informed by arrow. So you started out here, but now it got informed by arrow. So you see some of the green got over here. Maybe time influenced it as well. So now it's recoded a bit. This new encoding of flies now is closer. It got moved. It's closer to soars. Flies, soars. What happened over here? Fruit flies like a banana. All right. Then what happens here is that this gets influenced by banana, maybe some by fruit. So now this is going to be much closer to things that are close to that, that fly around those things. It's going to be like insect. So flies, soars versus flies, insect. How do you combine those things? That's exactly what self-attention is doing. Self-attention is the blending of the vectors which represent the meanings of the words. So self-attention, in a very crude sense, is really like an averaging of all the meanings. Remember, before we can do math on this space, right? Absolutely. We took king, we subtracted man, we got monarch. We added woman, we got queen. Well, if you can add, you can also average. And that's exactly what's happening here. You're averaging the vector for flies with arrow. It's not a straight average, 1-to-1. It's weighted. And what self-attention does is it does that weighting between the two. What questions do you have about this? Okay.
Sorry, I have so many questions. I'm just trying to come up with them.
I know. That's right. That's what my tea is for. I don't know if you noticed, but I drink a lot of tea when I'm teaching because it's
right
to give you a chance to do exactly what you're doing.
So this is where like I'm trying to wrap my head around this training process and self-attention and the fact that the generative models are predicting the next word, right? So it's using information from the future. Like it knows that arrow is coming to help determine the context for flies. But later down the road, if it's predicting time flies, like, how is it going to know what's coming next? Like, because in the past, it needs that next word for that weight to know what context flies is in, right?
So keep in mind that you put in a context, a big chunk of context, right?
Yeah.
You put in a big chunk of context. You never are doing just one token at a time. So big old chunk of context, that's where the self-attention works. Blending, blending, blending. So then it can get to the part where it can figure out what the next token is going to be for that entire context.
So it's like this phrase, it's not like it's just
all at
sitting
once
there in a vacuum. Like you're having this conversation about, you know, wow, we're getting older and man, time just flies by. And so obviously we're not talking about fruit flies, right? Because we already have that context of the conversation. Okay.
Right. And, you know, and depending on how your conversation has been going, it might be colored by, you know, regret or appreciation, right? I mean, this is very subtle. And self-attention allows for those very subtle, many-layered meanings to be imbued into each of the tokens.
Right.
And Holly, I was thinking this might be sort of appealing to you, you know, this idea that that rich meaning of each individual word is informed from the entire context. And this is why I think this is a golden age for humanities, because this is all natural language, right? And so understanding really what's going on is the realm of words and of meaning.
Jesse, can I jump in and ask a quick question there? So when it's doing the self-attention and blending of vectors, right?
Yes.
It's working on that through the entire data set, right?
Within a context.
Okay.
So, and that's the kicker. That's why context is so important. If you have a short context, but let's say you're, you know, you are doing crime and punishment, and you can only put this much in, right? But really, to understand what on earth is going on, you need to have all this, right? Well, then that's not going to work, right? The attention, that weighting, and the subtle meaning, you're only able to do it within here. That's why context length is so important. If the meaning is spread out very broadly, then you want to have as long a context as possible. But self-attention is expensive. There are limits to it. Let's go and take a look and see what this actually looks like mathematically, or partly mathematically. So we're going to pop down and this is basic, what's called single query attention. So there's a fair amount to unpack here. But we're going to go through just piece by piece, and then we're going to look and see what it's saying about attention. But let me check in. We've been at this for an hour now. Do we need a break, or are we okay to power through to 11 o'clock? Give me a green check if you're good to go. Give me a red X if you'd really like to have a 5-minute break. Okay, let's go and take a 5-minute break. We've been downloading a lot. We're going to start again at 10:06. And when we come back, we're going to talk about attention. See you in 5 minutes. All right. I'm going to go through with the decoder transformer and describe using the formal pseudocode what's happening in each of the steps. If it does not make sense, don't worry. The idea is that you get a better insight into what's happening, not that you understand everything about the notation. If you're interested in really diving into the paper and into the notation, I invite you to drop in my semester class. During the first 3 weeks, we actually go through this paper in depth. You're welcome to join in. If you're undergraduate or graduate student, you're welcome to register for the class. If you're a faculty, you can just drop in, and if you'd like to sort of dive into this a little bit more. But there's also another way to learn about this, and that is use GPT-4, especially. GPT-3 does it okay. GPT-4 does a much better job. BARD, I haven't tried, to cut and paste sections of the paper and say, explain this to me. And it actually does a really decent job in explaining what's happening. All of those are ways to sort of get a deeper dive into this. Let's go ahead and go in order, right? So here we have a decoder, and overall, again, what's happening, we get our text, we tokenize it, we do our encodings, we do our embed, we do our positional embeds, whatever that means, we'll find out in a moment. Then we have this decoder stack. This is where all the attention is happening, right here. Feed forward network is where things get learned. So this is the memory, the knowledge is here in the feed forward network. And we have a whole bunch of these. Then we have our hidden states, and then we do some things here. So let's go ahead and talk. Let's do this part right here. Token embeddings. So here we're going to have some token. This is a single V. This is a single token. So this might be cat, which might be token number 5. Because remember, we have this long context, and what we're going to do is we're just going to take it by token, and we're going to be coming up with its first token embedding. So the input is a number, an integer, which is from 1 to however many tokens you happen to have in your dictionary. And remember, tokens are set. Once you've trained your model the first time, your tokens are set. You can't change to another dictionary. So GPT 3.5, ChatGPT, you may have noticed that it's not quite as good with other languages. And if you do multiple language, you might notice that it runs out. You use up the context length is much shorter, especially if it's like Arabic or something. Man, its context length is really short. That's because the tokenization that they chose for ChatGPT way back when it was GPT-3 was not great for multiple languages. So you might have a single word, which is a single token in English, but to do it in Arabic might be like 8 tokens. So really not efficient. GPT-4, there were certainly more forward thinking to make it better at being multilingual and also multimodal, because you can also do images. So I have this long context. I'm taking a single token out of it. And what it's going to do is going to take that single token and it's going to return an embedding. Notice that E is a little bit bold. That E is bold. That means that it's a vector. So E is an embedding vector. This means that it is of length DE. DE is just a number that we choose. It's going to be, like for bird, it was 768 dimensions. So it's going to be a 768 dimensional vector of real numbers. That's going to be the E. So how does it come up with this? Well, what it's saying right here is it just looks it up. You choose a starting vector. You choose, you have the starting place for all of the different tokens that you might have, and it's simply a lookup. What's happening here is let's say, oh, this is number 5. Oh, let me look up the 5th one, and I'm going to return the token number 5, and here's its embedding. Straight lookup. Notice this. Notice what we have here. We have input, output, parameters, return. Input, what we put in. Output, what we expect to get out of it. Parameters. Parameters are, in this case, that parameter is the full lookup table. Given token number 5, what should be that first 768-dimensional vector to represent it? Well, it's going to be a lookup table. Where does this WE come from? Because it's a parameter, we know that during training time, it was learned. Parameters mean that it was learned. So we're not going to talk about the training, but assume that it has been trained. Lots of training took place beforehand, and so now we have our WEs. But what this means is somebody didn't choose this initial embedding. It was learned. So what does it mean when we go from our token encodings to our token embeds? This thing right here, token embedding. We're doing a lookup, coming up with our first pass guess. So for example, cat or west, let's do west. West is going to have the same embedding regardless if it's wild, wild west or west of here. Single word, west has only a single token, single lookup, so it's always going to end up right there. The rich meaning and understanding of what west really is doesn't come until later. So the first one is just a simple dumb lookup. Okay. Now remember, we have like wild, wild west versus west of here. Maybe position is important, right? So the fact that you might start a word with west is important, and you don't want to lose that versus where it appears as the fourth word. So how do you encode the positions? Well, that's what this does right here. Here we say positional embeds. And you notice this right here, the plus here? So you might think that this is like just saying, oh, and you include the positional embeddings. But actually, let's see what it's doing. Input. Input is going to be the position of the token in the sequence. So for the word, for Wild Wild West, L. Okay, so for Wild Wild West, what is L? And you can put it in chat or you can call it out loud. For Wild Wild West, what is L? Yes, that's right. It's going to be Wild Wild West. Exactly. Third position. For west of here, what is L? Exactly. So the output is going to be the vector representation of the position. So the positional embedding, again, is going to be just another lookup. It's another lookup table. And where does this table, which sort of tells you how you encode, it's learned. So again, now there are other approaches, other algorithms where they set it. In this case, it's learned. So, and one of the things that I think is just hilarious, it turns out there's a really simple way to combine these two, and we'll see those in just a moment. So William, you're asking, Wild Wild West doesn't become a token. It's probably going to be at least 3 tokens, maybe more, depending on what the tokenization does. But remember, each of those tokens is going to move, right? So Wild Wild West, at the very beginning, when you are first coming up with these original embeddings, they're going to end up in totally different places by the time you get done, because it's going to be averaging the different meanings. And so the positions are going to be closer to what they mean, like Wild Wild West. Wild is not going to mean, some mild statement about somebody, an observation that someone has made. Oh, that's wild. No, it actually means untamed, uncontrolled, right? Because of the context. are there constraints for I max or L max? Yeah. So so L is going to be your maximum token length, your maximum context length, and that is set with the algorithm. Once you have set your context length, you can't change it. It's computationally very expensive, and so it tends to be smaller. But there are some solutions now which give you much longer contexts. All right, so there we're all the way up to we're all the way through here to the positional embeds. Now we need to go into the decoder stack. So what happens on a decoder stack? We have an embedding that gets put in, and then we have attention. And then in this case, we may or may not have this attention, depends on whether this is part of encoder, decoder, or just decoder, but we have the attention. So let's talk about attention now. What does attention look like? So remember, the point of attention is we need to blend these things. So we need to combine the meaning between different vectors. So this is what's happening here. What's the input? We're going to have the embedding vector goes in. Oh, and yes, Shane. Yes, they're really added together. It's hilarious. And I'll talk about that in a moment. So single query attention. So we took the embedding comes in. The other thing that goes in is the vector representation of all the rest of the encodings. The one for wild, the other one for the next wild, because remember, they can be different. One's wild in position 1, the other is wild in position 2, and the third is west, right? So you're going to have the embedding for west, but you're also going to be seeing the embeddings for all the other things in your context. The output is going to be a brand new vector representation of the token and the context combined, a new representation for west that is informed by all the other tokens. What are the parameters? Well, we need to have we need to have a number of different things. Where do these come from? We don't even know what they are yet. Some W, and by the way, capital W bold means it's going to be a matrix. Lowercase bold means it's going to be a vector. So can somebody tell me where these come from? Yeah, now they're going to be used in the neural network, but where do they come from? Let me ask you this. Did somebody set these? Did somebody go in and say, here are the numbers we're going to use? No, that's right. They're learned. Exactly. They're learned. How do you know that? Because it's parameter. Parameters are learned, which means, and this is the really wild thing, we're allowing these parameters to simply go to wherever they need to based on training, right? So we'll talk a little bit more about this next week, but deep neural networks, through backpropagation, learn. So you can think about everything that we're talking about, everything we will talk about is an architecture that we just set in place, and then we let the network learn. At no point are we directly programming what these embeddings should look like. We're creating the architecture, we're saying what are parameters, and then we do training on it, backpropagation. We say, hey, here's a whole bunch of data, self-supervised learning, backpropagation, go and learn. Figure out what WV is. Figure out what BV is. Learn it. So what happens with this? This is sometimes called QKV. I'm going to unpack this just a little bit. What's happening here is that we're taking the token, we're transforming it a bit. This is a linear projection. And again, if you don't understand what this is, not a problem. It does a linear projection of Q. Then we also have, we're taking that same embedding. Notice we have the E. This is the Q is going to be that target, west. Here we have all the other ones for the full context. So here we have K is going to be for the full context. Then V is going to be, again, the full context, but with another embedding. What's happening is, and we'll do this sort of visually up here, is first we're seeing what flies is closest to. What was closest to it first? Then what we're going to be doing is we're going to be doing averaging based on how close they were. So what we're saying here is, what we're essentially getting here is, we're getting how close are they? That's what this part here is doing. How close are they? And then we're doing a weighted average. We're doing a weighted average. So visually, this looks like flies at this point was closer to time and to arrow than to like and to and. Therefore, when I average these together, arrow and time are going to have a heavier weight in the weighted average than the other parts. So it's not a dumb average of, oh, everything gets averaged together. Instead, it's those vectors, those points, which happen to be closer earlier on. Now remember, I'm doing a projection, right? So I'm already moving the points a little bit in some way that's informative. And then when I move them, now it's going to be closer. So now I'm going to do a weighted average, which is quite literally an average. And now I've moved them. I've blended them a little bit. So as an overview, does this make sense? What questions do you have? Michael.
I guess I have a quick question here is that when we talk about this transformer algorithm, are we talking about the pre-learning, pre-training, or we're talking about the generative part?
So here we're talking about basic architecture, and we're assuming that we've already done our training.
Okay.
The paper does talk about training and how it works, but here we're just assuming we have a W sub Q. Got it from somewhere. Oh, we learned it. It was learned previously. Now it's just a vector. It's just a matrix that is available to you.
Right.
So now those things are available to you. We've already done our training.
I guess that's kind of my fundamental question is that when the pre-training was done, it is using the transformer.
Yeah, so think about this. One way to think about this is when we do training, we allow the parameters to vary. When we're doing inferencing, when we're actually just running it, when you're actually interacting with GPT-4 and you're saying, explain to me the following, it's fixed. All those weights are fixed. Its training is done. And all you're doing is underneath the covers, all that's happening is doing all those matrix multiplies for you to come up with the next prediction. There's no training whatsoever.
Of course, yeah, I get that part. I guess I have not looked at this paper as a whole. I would assume for the training part, it should have some kind of back propagation somewhere.
It does,
right?
yeah, that's right.
Okay.
And so it talks about back propagation. And the only important thing for us to keep in mind here is that know where the parameters came from, because that's something which is often confusing. So where does that W sub K and the W sub Q come from? It was learned during the process of training. It is fixed now. Yeah, Joshua.
Yes, on the big picture that you had of the overall encoder, you end up with one vector for each of the input tokens.
Yes.
But through this whole process, they all sort of get massaged together using the self-attention.
Yes.
Does that n vector kind of represent everything about the context, or is there still some link between the first vector is somehow linked to the first token, Or is that all just kind of
no, you still
together?
have that. Yeah. So I mean, because think about what goes into. So what's going into each of these is the input is going to be that embedding. That embedding for all the different tokens continue through. If you start with 20 tokens, you start with 20 tokens right here, 20 tokens, 20 tokens, 20 tokens. Now they're 20 tokens with their long embeddings, right?
Right.
This sends 20 tokens and they're, the embeddings, 20 embeddings. Now it's 20 embeddings, right? All the way through 20 embeddings to 20 embeddings.
Okay, but if I had taken that context and sort of told the story in a different way, but captured the same meaning, would I expect that my output state would be similar or the same?
It's going to move them. So, and remember that the thing that you're going after is what you're asking the decoder transformer to do is to predict the next token. And it's very likely to predict tokens that are in that same area, because it's going to, even though this may be a long roundabout way of saying it, right? Or you might have a shorter way of saying it, or it might be two different languages. But if it's meaning the same thing, then yes, it will have moved them. And so the tokens are going to be in the same neighborhood, quite literally, regardless of how you got there.
Okay, thank you.
Cameron.
Yes, thank you, Jesse. It's really interesting to think how it learns, and then how it increases its weighting. So when we're in chat now and we ask it something and we like it and we reward it, we give it a thumbs up and we say, yes, this was great. Mm-hmm. Does that that moment it adds to its parameters? Not
because it's too expensive to do that. And there's a type of training that happens at the very last, which is called reinforcement learning from human feedback, which is a way of really willy-nilly changing those thetas. Oh, so okay. It changes everything. So at that point, you can't really do additional training on it because it would destroy the reinforcement learning from human feedback. So, but what they're doing is they're storing that. Gotcha. And so what they're saying is, oh, see, it's perfect training data, right? You ask it to do things, it did this thing, and you gave it a thumbs up. You said, that was good. Yeah. That's going to be really useful later for additional training of the next generation of model.
Oh, I see. Okay.
Yeah.
Okay. Thank you.
Absolutely. And Joshua, did you have another question or just need to put your hand down?
Sorry, I meant to lower my hand.
Great. Oh, okay, great. All right. So we're all the way through here. We're into attention. I'm going to keep this high level, but that idea of attention, here on the left, we have basic attention. On the right, we have masked attention. So in this case, we're just doing averaging here. What we're saying is, oh, we're going to blind ourselves to some of it. Masked attention is how you do the training to blind yourself to things that come later. So this is generative pre-training. The heart of it is masked attention. So this is a way for you to say, hey, I'm going to not let myself see the stuff that comes later so I can learn about to use just the information up to a certain point. William, you have a question?
Yes, well, I guess it's related to one of the earlier questions, but one of the questions that I asked recently to Bing Chat was, can you list 10 pet safe plants for the yard? And it came back with a list, but some of the plants that it came back with were not pet safe. Like if the cat were to eat it, it would get sick. I know that. So you can put like a thumbs down, but like that's not really meaningful because some of the information is good, but some of it's not. How are they capturing that type of information, and how is that used in these models to really kind of understand like errors? Like how are they going to, anyway, so maybe it's unrelated to your current conversation, but it's related to one of the questions that came up earlier.
Yeah. So they could use the information in a number of different ways. One is, for a lot of that, the thumbs up, the thumbs down is more likely going to be used in reinforcement learning from human feedback. So way back up here, you remember when we were talking about this part right here, where what we're really trying to do is to figure out that distribution of the next most likely tokens. That's the heart of generative AI. That what we have is we can give it the context and the thetas. The thetas can be changed based on back propagation. This was the next word, this was not the next word, or through reinforcement learning of human feedback, which is this was preferred over this. This got a thumbs down, this got a thumbs up. That kind of training changes a whole bunch of the thetas all at once. And that's why it's reinforcement learning. So you're right. Is it going to be as useful for supervised fine tuning where it got some information wrong and so it was predicting the wrong token? It'd be hard to. But could it be used to say this is an example of a good response versus this is an example of a not so good response? It might be useful for that. But both are ways of changing the thetas, and so you can improve the output.
Thank you.
All right, other questions? Okay. Let's go ahead and dive into, I'm going to skip over this a little bit. Well, I'll mention this. So this is from basic single query attention. We add the idea of masking. So here we have masking. Then the other thing that we go to is called multi-head attention. So transformers have multi-head attention, meaning you might have an attention head which is concentrating on, has learned to concentrate on parts of speech. Another attention head may be, so you can imagine the blending happening here based on part of speech. It may learn that, or it may blend based on more having to do with meaning or with syntactic similarity. These are free parameters. We're letting it learn whatever it wants to. But by having multiple attention heads, you can have the model attend to different aspects of a way of blending the meanings of the words all at once. So you can imagine if you only have one attention head, it's going to blend in a certain way. If you have multiple attention heads, then it makes it richer, and maybe it can attend to, oh, I'm going to blend based on part of speech, what goes together, or I'm going to blend based on this other characteristic. Maybe I'm going to blend on style of writing. Could be anything. We're letting it learn. So the fullest version of this is multi-head attention. The only thing that's different between them is whether or not you choose to do masking, how many heads you choose to have. So what's happening here? This is called scale dot product attention. I'm not going to try to go too much into that. Let's go ahead and take a look at the whole deal, the whole generative pre-trained model, the whole decoder transformer. This is it. To the left here, this is the entire. This is the heart of ChatGPT and GPT-4. All these algorithms look almost exactly like this, with some changes in parameters or hyperparameters. So what's going on here? Input, we have a sequence of token IDs. This is your context. Could be a sentence, could be a paragraph, could be a whole page. We're putting X in. X is going to be our words, our context. What's going to be the output? The output is going to be a probability distribution over what the next tokens might be. We now know there's going to be some additional processing, and it's going to string together a number of these, and so it returns a whole sentence. How many of you have used GPT-4? Give me just a quick thumbs up if you've used GPT-4. Okay. So Cameron, does it just like give you everything all at once, or is it slow?
Oh, sometimes it's very slow. It's thinking. Yeah.
Yeah.
And it'll go.
Exactly. And Holly and others, I will show you how to get to GPT-4 right at noon, right during the office hours if I can. So Cameron, you're watching it actually predict. You're watching it generate its beams. You're watching this algorithm play out while it's generating.
That's cool. That's what it's doing.
That's what it's doing. So input is the context. Output is that probability distribution from which it chooses what the next token is going to be. The hyperparameters, these are the things that you get to choose. What's going to be the maximum context length? That's L max. How many layers? How many of these different, you know, when we saw these before, you know, you notice that when we did this, we had like ... Well, how many of those things do we want? Well, that's the number of layers that you have. That's going to be, that's encoder, decoder. That's going to be your L. That's your L hyperparameter. Hyperparameter means that you have to choose it. The size of your embeddings, you know, a bunch of things that you have to choose. What's going to be learned? All of these things are going to have been learned previously. And that's where all these things came from. So let's see what happens. Here's the algorithm. It's numbered just 11 steps. Step 1, you figure out you get the length of your particular context. Then what we do is we go ahead and we come up with our first embedding here. So we come up and we do the embedding step. That's going to be right here. We're doing this embedding step right here. This also is in doing the positional encoding. Now, this is hilarious to me. This is that encoding step, the token embeds, this is the token embeds right here. This right here is the positional embedding. And you see how it's combining the positional embedding with the first embedding? It's adding them. That's so funny to me. It's like, so it's like, oh, I'm going to add just a little number that's going to represent where it was. It's not going to be adding a whole 1. It's going to be like, if you're in the first position, I might add a 0.01. If you're in the second position, I might add a 0.002. And so that's how it's doing the position encoding. Then this is where we start getting into the decoder stack right here. What do we do here? Well, first, we're going to do something that's called a layer norm. It's just a way to bring the numbers down so they're all on the sort of the same range here. Then we're going to do our attention. We're going to do the blending of all the different vectors that came into this. Remember, we have one vector for each token going into this. Then what we're going to do is we're going to do another normalization. We don't want the numbers getting too wild. So we're sort of going to bring them all down. Then this part is the feed-forward network. So here we're doing the blending, and then we're doing the feed-forward network right here. This is where all the learning is. So we're actually feeding into the network, presenting it to the network and saying, hey, here's the meaning currently. Give me a new meaning based on where I am right now. So it reinterprets and gives you a new representation that uses this feed-forward network. And then we loop and we do it again. Then at the very end, this is where we get the probabilities out. So that's it. That's GPT. That's ChatGPT. So remember I said that it was let's go to I'm going to pop back and forth between these two. This is the encoder transformer. This is the decoder transformer. Do you notice something about these two algorithms? How much is changing between them? Okay. So first of all, are the hyperparameters and parameters changing very much at all? Very little, right? So the parameters are almost the same. And look at step 1 is the same. Step 2 is the same. Step 3 is the same. Step 4 is the same. 5 through 8, notice that all that's happening is that they're doing them in different orders. If you look closely, the masking is different in the multi-attention head. Here's decoder transformer. Here's encoder transformer. So encoder transformer, notice the mask says is 1. It's not doing masking. It's allowing everything through. Decoder transformer, it is doing masking. And what it's saying right here, a way to interpret this is, hey, you don't get to look at anything beyond this token. You don't get to look further. When you're doing the blending, only blend up to the point that you had. That's the masked attention. So up to this are almost exactly the same. It just has to do with the attention heads acting differently. And then we get down to the end, and it's almost exactly the same. So this is kind of mind-blowing. This means that when we looked at the family of these models that seem so drastically different, the GPT models, you know, the Chat GPT, versus the things like BERT, which can be doing 2 totally different things, actually at the heart are almost exactly the same. The attention heads have different parameters. The order in which you do the normalization is different. The training is different between them. So this speaks to the fact that transformers are really very powerful general purpose learners. You can slightly change how you're training them and get very different kinds of behavior, but the transformer, the heart of it, the idea of having attention combined with the feed-forward network in this way, where you have them stacked up like this, turns out to be a terrific solution for general purpose learning. So, to what do we have to thank, you know, our new age of AI? It's the transformer. And even more explicitly in there, it's self-attention in a deep learning network. Self-attention meaning you combine multi-head attention that we've been talking about with feed-forward networks in stacks like this. That's why it's called self-attention. It's, you break it up. A layer of attention, feed forward, a layer of attention, feed forward, a layer of attention, feed forward. And it's not just the graphs that look the same, it's the algorithms are very much the same between the two. Let me pause here. What questions or observations do you have? Shane, you had a question. Does punctuation undergo token and positional embedding? Depends on the tokenization. Usually not. Usually, though, a period, any end of phrase is encoded as with an end of phrase token. But beyond that, depends on your choices. You could or you could not. GPT-4, we don't know because they don't say. Does positional encoding add noise? Usually not. Usually it's informative. And think about it, it's just putting a clue into the embeddings. Whether or not the model learns it is dependent on whether it's useful. All you're doing is you're flavoring the embeddings with some positional information. And if the model finds it useful when it is undergoing training, then it will be used. If it is not informative, then it's not going to be used. Michael.
Yeah, I guess I'm trying to see in this architecture, for example, you know, we talk about, you know, lambda is like 60 billion parameters, and ChatGPT is about 130 billion or whatever.
Yes.
I guess in this architecture, how like this head or where those parameters actually get, I mean, just like your point, right?
Great
you know,
question.
every algorithm, fundamentally, they're just doing this transformer, but they somehow are able to say, I'm 60 billion parameters.
Right.
Where all the parameters can get calculated? I think I read a paper, I can figure it out, but I think it probably is a useful thing to talk about here as well.
And actually that's why I love the formal algorithms, right? So if you think about it, there are only so many parameters that you can have for attention, right? If you're limited in your length, so one way to get more is to get longer and longer length. That's one way to get bigger. But think about the layer norms right here. I'm sorry, no, the GALU right here. So right here, this W1 MLP1, if you want to take a look at it visually, it's going to be that GALU, that sentence, that part was the feed-forward network. That's the part that grows. You know, you're not going to be able to get that big with your position embeddings, right? You're not going to be able to get that big with your attention because, you know, there's only so much you're doing. But feed-forward network, that can be as big as you want. It can be as many layers as you want. It could be as wide as you want. You know, you can go in and take a look at the parameters yourself a little bit later, but you can, that feed-forward network can get huge. That can grow without bound. That's what gets big. So with BERT, you know, you might have a couple of million parameters, maybe a couple of 100 million parameters. But with GPT-3, you can have 175 billion parameters. And where are almost all those parameters, that growth coming from? The feed-forward network. As that feed-forward network gets larger, it can learn and learn more. It can have richer and richer representations. It can store more information. Remember, it's not a database, but it can learn a lot more about the relationships it finds in the text it's given. And this is its representation of what is found in the text. So if you want it to be able to learn more, to understand more, you make the feed-forward networks much larger. Almost all that growth is in the feed-forward network. Laura.
Thanks. I have two questions. The first, is the beam search, is that something that happens in the positional embedding, or is that part of the decoder?
It's actually after everything. It's not even represented here because it's not a core part of the transformer architecture. This is more like your choice that you may program to do with it afterwards. Okay, got it. And then the second question is, why are there multiple decoder blocks within the stack? What does that represent? So that is actually, that's the secret sauce. If all you had was one attention and then a feed-forward network, we've done that. And it learned that it wasn't a general purpose powerful learner. It turns out that part of the secret here is to have what's called self-attention. So for each of these blocks, and remember, this is a capital L, how many layers you're going to have. Because if you think about it, okay, I've enriched the representation up to a certain point. Let's do it again. Let's do it again. Now let's do it again. And each time you get a richer and richer representation. At learning time, when we're first setting this up, it allows it to learn much more deeply because it doesn't have to capture everything at once. So it's not all is not just depending on this one set of attention heads and this one set of feed-forward networks. No, you can have a totally different, another take on it coming up after. And that turned out to make all the difference. Got it. Thanks. Absolutely. Michael.
What is hidden there? I think we kind of almost like treated hidden there as is something, but what is it actually?
Sure. Let's go to the algorithm, right? Because this is why I love the formal algorithms, because it's like, well, what is a hidden state? I don't know, it's hidden, you know, but if you have the algorithm in front of you, let's see what actually comes out. So at this point, you know, this is when we get to this point right here, We've done all of our layers. So at this point right here, we are right here. So at the end of that loop, we're right here. So let's see what's coming out of this loop for the decoder. Oh, it's just all the embeddings. It's just all the embeddings and where they ended up. So if you went in with 20 tokens for your context, you have 20 vectors of the length dimensionality of your hidden. So for BERT, it was 768, 20 768. You end up with 20 768 dimensional vectors. That's it. What is it? It's a matrix, 20 by 768. We call them hidden states. All that it is your final embeddings that you ended up with.
Sorry, where did 756 come from again?
Hyperparameter. Yeah, that's a hyperparameter for the and just to be perfectly, so BERT is going to look just like this, and it is going to be the hyperparameter here, which is going to be the DE. You see that DE right there?
Ah, okay.
That's your DE. That's the length of the vector for the embedding. The DE, the dimension of the embedding. So the dimension for the embedding for, let's go to a decoder. So this is GPT. So this is going to be the another DE, but this one could be like several thousand. For GPT-4, it's probably several thousand. So it's a much bigger embedding. Where does it come from? It's a hyperparameter. Someone chose it. Someone chose all of those numbers before they started their very first training. And then that's what we're left with from that point forward. Once you set a hyperparameter and once you start your training, your lookup vectors are set. Everything is set, and the models are simply going to be learning all the parameters on top of that. Laura, did you have another question, or great, yeah, not a problem. Other questions?
I guess I have one. Based on what they've learned in the initial GPT models, what have they learned about software development in terms of how to better foresee what vectors or features are going to be most important, and how to allow for changes down the road?
So that's a great question. I think what we're entering now is we're going to be able to start directly learning from and inspecting the embeddings, first of all. A lot of this up to this point, really, Doug, has been, as you know, has been really empirical, right? Not a whole lot of theory behind where do we go next. Up to this point, transformers, self-attention was a discovery. Oh, we've tried this with attention. We've tried this with attention. Hey, this seems to work. Oh my God, this really works. So now we're starting to explore in a much more systematic and theoretically motivated way where to go next. Like we've been exploring how much training do you need versus, does it help that your DE is large, or that you have a ton of layers, or that your feed-forward networks are huge, or do you need more training? And what we've learned empirically over time is that more training is more important. You can have smaller models architecturally and still have them learn a great deal. That's what we learned from the llama models. But a lot of this is still empirical learning, but now we're starting to do more theoretically motivated exploration. Victor, you had a question, then Holly, I think you had a question too. So Victor, where does daydreaming come from? Feed-forward networks are deterministic. Yes, but daydreaming, first of all, remember that when we are doing this step here, let's do this. When we're doing this step here, yeah. At this point, let me go up to here. Well, I have this little classification head. I wish I didn't, but generating next words here, we do add noise here, right? So we're adding noise at this point. So it's not just, if all we did was just generate and chose the highest probability token, it's not that interesting. It's not that good writing. So we inject some noise there. We choose maybe out of the top 10, or we, there are various ways of doing this to add variety into what's going to be generated next. Second, when we say daydreaming, sometimes it's called hallucination. And the idea is that it's generating things that aren't true. Like somebody was just mentioning, give me 10 plants that are pet safe, and it generated 10 plants, but not all of them are pet safe. Remember, these feed-forward networks, these are not lookups, right? This is just generating what is most likely. If we go back to what we're talking about with over here, which is the task, the sequence modeling, hey, all it's doing is coming up with that probability distribution. So it's coming up with a probability distribution. Is it absolutely factual? Well, it's giving you things that are likely, but it's not necessarily going to give you things that are exact, that are lookups, because it can't do that. So how can you improve what it's generating? Well, actually, if you think about it, you're not going to be changing the thetas, right? That's training. That's not going to take time. So how do you get more accurate answers out? It's all about the X. It's all about the context. So what's happening now with models when it does a web lookup is it generates its first answer, realizes that it doesn't have enough information. So it goes out and does a web search, injects that into the X. So all of the plugins that we're hearing about, the web browsing plugin, the Alfred Wolfen plugin that I was mentioning before, all of those are changing X. They're augmenting X. They're augmenting the context. They're taking your context and they're adding more information into it, so it does a better job of predicting what the most likely tokens are next. So if you say, hey, I want to know what some plant-safe things are, and it gives you a crappy answer, an augmented model, and what Bing was doing was just going out and doing it like a general web search. If you did that with Wolfram Alpha, it's going to be doing a query against Wolfram Alpha on animal toxicity in plants. And it's going to come up with a whole bunch of information that it's going to go back and put back into its context. So it's going to look like, hey, give me 10 plants that are safe for pets. And then it's going to give you a whole bunch of context on toxic plants, plants that are toxic to animals. And then it's going to rerun itself. And now, is it going to give a better answer? Yeah. Why? Because the model learned more? No, learning has ended. X is better. X is more constrained. It has a lot more information about toxic plants now in its context. So that's what plugins are doing. Nathaniel.
Hi. So I had a question about the hyperparameter L sub max, which I understand to be the maximum sequence length.
Yes.
Which I understand to be related to the sequence encoding. Yes? No?
Only pragmatically, right? So the length is going to be, that's going to be like the hard limit that you set at the very beginning, because that's going to determine how much compute you're going to need to have. Because when you do the comparison across all the tokens, it's got to compare all the tokens pairwise. It goes up with the square of the length of that. Because when we talked about, oh, it looked small when we were doing it. It didn't look that imposing. Oh, you're just doing this thing right here. That's actually a ton of compute. Because you're doing this whole vector with this whole vector, boom. And there are ways that you can ameliorate that, but that's what that context length says.
Gotcha. Okay. So maybe that's not the right hyperparameter to answer my question. My question kind of boils down to this notion of positional information. So I have a token that's in a particular position, right? And its position has meaning.
Yes.
But it feels like there are limits on the meaning that position can have. Say if you had 3 sentences in a row, and you were trying to determine,
yes,
you know, the position of the word flies in the first sentence,
yeah,
right? And so the fact that it was first out of 100 tokens,
yes,
but the sentence ended after the 9th token.
So Nathaniel, let me do this.
Yeah.
I'm gonna let me answer your question in just a minute, because what I'll do is I'm gonna move into office hours in just a moment. Very interesting and multifaceted answer, and surprising as well. So if you'd like to know the answer to Nathaniel's questions, stick around for office hours. So what have we learned? First of all, this is where the encoder decoder transformer first came from. This is why it's named encoder and then decoder. Those are just names. The encoder transformer all by itself is dead useful, often used for classification, question answering, things like that. Decoder transformer is all of the GPTs that we have. So that is all that architecture right here, just the second half of this architecture right now. They operate independently. They don't need the other one to operate. We've seen that actually the algorithms are very, very similar to one another. That when we talk about the architecture, we're talking about how many layers you're going to choose, what their embedding size is going to be. Those are all choices that you make, the hyperparameters that you choose that define the architecture of what's going to go into your model. What else determines the model? Well, the data that you train it on, how much you train it. Architecture is only part of the story. The other part of the story is how much training and what kind of training you're giving it. So does the architecture change between a single language model and a multi-language model? Nope, not at all. Does it change between a single modality model or a multi-modality model? Nope, it doesn't matter if you're learning on words or learning on words and images. So long as you have a tokenization scheme, it's just learning of the tokens. And it learns by which tokens it is. Oh, you're showing me a picture versus, oh, you're showing me text. Transformers are powerful general purpose learners over any sequences over time. Any sequences over time. So it doesn't matter if it's multiple languages, multimodal, it can learn. This is the heart of the AI revolution that we're seeing right now. And the heart of that revolution is this very humble attention mechanism. And now you have a good understanding of what's there. If you want to dive more into this, work with the paper, work with GPT-4 in the paper, and ask questions about it so you can get a better understanding. You're welcome to join me in our semester class. We offer it every semester on transformers. The first part is very much around understanding the architectures. Love to have people come in and sit in. Very happy to have people sit in. Or again, if you're undergraduate or graduate student, you can register for the class as well. We're a little bit over time, but let me stop right here. Let me answer any last minute questions that you have. If it's a longer question, we'll go into office hours, but any sort of final wrap-up questions? All right. We are going to be tomorrow talking about what I was mentioning before about how to augment the output of these models, which is all about getting more and better X's, more and better information into that context. We're going to be talking about Lang chain, which is a way to go out, seek, get, and inform. All right. See you all tomorrow. Stick around for office hours if you'd like. All right, so Nathaniel, you were asking about position encoding. First of all, let's go into the algorithm. Let's do the decoder transformer. Because I really think this is funny. I laughed hard when I saw this for the first time because I didn't understand how does positional encoding get in there. And the answer is, first of all, you do a lookup into some table. Where does the table come from? Most common way, it's learned. So over here, the positional encoding, you get the position of your vector, you look up the embedding vector, and you're done. So I'm the 5th position. Great. Let me look that up for you. Here's your 5th position in coding. How do you include that in this really subtle, embedding? And, how does the meaning of position interact with the first encoding, the embedding that you have? Oh, yeah, that's right over here. We add them. We add them. Here's the semantic vector, the semantic embedding. Here's the positional embedding. Add them. That's it.
Okay, I got that. The thing that feels important, but maybe isn't actually important, right, is this notion that we have to set a maximum value that position can take. And I think that to mean that we're going to arbitrarily decide that number is 100. And so things can be in the 1st, 2nd, 3rd, 4th, or nth up to 100th position, right?
Yeah.
Which then I take that, that position, the 54th position. I go to our learned, dictionary of position embeddings, and I get it. Right. So now I have this vector, which is the same length as our feature vector, right?
Yeah.
So I can add the two together and boom. Okay, great. And maybe this is just hyperparameter tuning, but sentences in English are 15 words long, right? So if my sequence contains multiple sentences, right, 4 of them,
so
then
you're talking about hierarchical position encoding, perhaps. That might be one way.
Sure. Okay, I got you. So it is not necessarily the goal that L max be equal to the average length of an English sentence, such that positional encoding has meaning for where a word appears within a sentence. That is not the case.
So remember that this positional encoding is just one particular architecture, right? And there are others. And William, if you're still here, the homework really is to familiarize yourself more with the paper. This is sort of a special one-off here. So reading the paper would be the homework. So positional encoding could be done in many ways. As a matter of fact, one way of doing this is one way that's not learned at all. Oh, there you are, William, you're right there. Is to sinusoidal. And this sort of gets to your notion of locality, right? So is it informed by, the average length of sentences in English versus murmur? No, we're just going to do a sign. All right, here we go. And we're off to the races. Is it useful? Does the model learn on it? Right. And so really comes down to a positional, I'm sorry, to an empirical question. Does it help the model learn better or different? And there have been many different schemes that have been explored where you keep all the rest of the architecture the same, but you might change the positional embedding scheme, where you might do one which is hierarchical, where you encode information about its position in the sentence and its position in the document. So which sentence is it in? Which word in the sentence is it? Which sentence in the paragraph is it? Which paragraph in the document is it? And then is one better? Train it up.
Sure, understood. Got it.
See if it gets used. Because remember, it's like you're almost like putting little breadcrumbs out there, right? Positional encoding is breadcrumbs for the algorithm. If it's useful, it'll learn it. If it's not useful, it'll just go away in the statistical wash.
Got it. Okay. So so for example, the tokens that construct in conclusion, right, are very likely to appear at the beginning of the final sentence of a corpus of
So
text, right? If you have a classically structured essay.
Exactly.
Right. Okay. That's what you're saying. Okay.
Gotcha. So it might say, oh, wow, that's really useful to know.
Okay. Gotcha. But positioning, the mechanism by which you determine position can be quite nuanced and does not need to be this kind of single, single vector Okay,
Right.
got you. Okay,
And
understood.
the thing to keep in mind here too is that this is the stupidest way possible you could do this, right? The
Sure.
stupidest way.
Right.
And it's highly effective.
Okay, understood. Thanks.
So to me, what that means is it is learning, and the learning mechanism is powerful enough, and those representations are powerful enough that even if you give it the stupid breadcrumbs, it still is enough for it to learn on. Other questions? Go ahead again, Nathaniel. Absolutely.
All right. Sorry. Okay. So I am working these days with a model called Segment Anything, right? And I have a much better handle on how that model is constructed after, at 11 o'clock today than I did at 9 o'clock today. In the sense that there's an image encoder piece. So there's an encoder transformer that sucks in images and creates these hidden states that represent that new image. And we've futzed around with it enough to know that hidden state data is slightly larger than the image itself. Like on disk, an image is yay big, and then the hidden state data representing that image is like, right? Right? Yeah, exactly. So it has this image encoder. So there's an encoding transformer that consumes images and creates this hidden state data. And then it has a prompt encoder, which creates some other interesting hidden state data. But that is very tiny. Like the encoder transformer that represents the prompt encoding is minuscule, and you can run it in a browser even. And then there's a decoder transformer that creates masks. Right, from it. So I think that I've learned today that this decoder transformer is a model in its own right, and the prompt encoder is a model in its own right, and the image encoder is a model in its own right. I think what's less clear to me is, okay, great, how do these all get stitched together so that they do something useful, especially in the context of multiple encoders, right? I mean, am I just adding these two things together? Okay.
So here you'll notice that we had the encoder and decoder. So essentially two totally different models. And the only place they make contact is right here. This is the KV from the attention. This is called cross attention. So this is the part of the attention that I glossed over a little bit because it would have been too much in 2 hours. I already jammed as much as I could. So cross attention is you attach the two attentions. So rather than looking across your context and looking for similarity just in your context gets broadened to the context from the attention from the previous model. So it sets the KV, and that's how it communicates. If you train both of these together, if you're training them together, then the weights learn together. So the communication during training is what works. Back propagation across all of them. They begin to learn similar representations, or at least representations that are yoked together in this manner. So now when you say, select all of the inner structures, that has meaning in the representation, that graphical segmentation representation, because they got trained together. Does that kind of make sense?
It does. And funny side note, as far as we can tell, the prompt encoder does not handle natural language well at all.
No.
It will take,
which is
points.
why it's small.
That's why it's small.
Right?
Yeah, I got you. Okay.
It doesn't know the language.
Right. Okay. It'll take points. It'll take boxes, but beyond that, it doesn't understand what you're trying to ask it to do.
Doesn't a whole. Yeah, exactly. That would be and diffusion models. You'll notice, like a stable diffusion, you could just use keywords. Whole sentences don't matter there because it also is having a sort of a reduced representation. Now there are models that do much richer, where you can say, you know, you have a natural language, you can say, choose the dog that looks sad. Great. It has the full representation and the images trained together. They tend to be much, much larger models, but there are models that can do that. But segment anything is not one of them. William.
Yes, my question, it has to do with, in the paper, it talked about how it sometimes takes tokens apart. I know I asked a question earlier about whether it goes back in and ever looks at the tokens that it has and tries to kind of group them or anything. But it doesn't talk about that, but it does talk about how it kind of takes tokens apart sometimes. Like it takes off like the endings of words, for example, sometimes. And
Oh, you mean so words. So this is the so in particular, you're talking about the tokenization. Right? It's almost a step before this.
Like the word Western, for example. Like you kept talking about West, and you know, and but like I think like Western philosophy is like quite different than like Wild Wild West or
sure.
You know, and so does it cut off that ERN and just say like West, or does it treat it as like a totally separate word, or?
It preserves everything. So you can undo your tokenization completely. And there are some things that like diacritical marks, depending on, you know, some punctuation may or may not come back out. But tokenization is something that you do once and you do it before you do any of the model work. And often it's a statistical question that you're answering. What tokenization scheme could I come up with such that I capture most of the words with single tokens? I allow a certain number to be represented by 2 tokens. You know, and in the worst cases, I want to have 10% or less that require 4 or more tokens. Statistical question. Crank through a sample of your data, come up with different schemes, and then you land on one. And it really is a lookup. Whenever you see WES, that's a token. Whenever you see TE, that's another token. SAT, that's a single token because, you know, SAT appears all over the place. Or AM. AM is all over the place, so it gets its own token. So what it looks like if you were doing Western, remember it's not encoding semantics yet. It's just breaking it into tokens. So it might be WE, it might be WES. Okay, that's 42. TEREN, okay, that is 986. Space, there might be a special token for a space, you know. Great. Now I want to, and some of them there's an encoding scheme where I say, oh, keep with the next token. Some models do it, some models don't, or some token schemes have it, some don't, where it says, oh, keep this together. So West needs to stick with turn, or just allow them to be free floating. You could do either way. Is it capturing the meaning at this point? No. All you know is you have 43 and whatever the other 932, whatever the other number was. So what goes in at this point? 43 and 932. Then what happens next? Now you look up what is the vector that goes with 43? What is the vector that goes with 932? Then we begin. So the tying together happens later here.
Okay.
Yeah. So there's not a whole lot of meaning. There's like, now the other thing you mentioned, like stripping off the ends of words and things like that, that is older NLP. That used to be how we do it, how we used to do it. You know, sometimes called lemmatization. And, you know, it was like the only thing we knew how to do. It's like, well, run, if I want to get run, running, runner, and I want to pull them together, maybe I just chop off the and the ing and the, you know, and I just keep run. Well, it's no wonder that it didn't work all that well for subtle meaning, right? Because running, runner, run up, all got encoded as run. So, and it did not work the other way, right? If you tried to undo lemmatization, too bad, so sad. You've lost it. Undoing tokenization, yeah, you can get all of it back except for the things you never tokenized, like, you know, parens or things like that. Does that kind of make sense?
Yeah, I think it does. Yeah, and so it'll store like parts of the words, but it'll group like But you're not like stripping off the ends of it so much.
Right.
Yeah.
You're breaking them apart.
Right.
Really, that's really what you're doing. So interesting things can happen, like the original GPT 3. For medical notes, patient. I think it's something. I don't know if it's that tokenization scheme or another. Patient. The word patient, single token, could be a single token, right? PT, which is how doctors refer to patients. PT presented with is 2 tokens, P and T. So it actually is harder to learn ideas about patients when they use the PT versus patient. So, and they do, eventually it learns, because remember we have lots of layers here. And so it eventually glues them together semantically. P, T ends up in the same space. Both P and T become, encoded in very much the same way, meaning, by the way, it's very close to the code for patient, but it takes a while to learn it, and the representations are harder. So tokenization can influence how easy or how hard it is to learn particular languages, particular words, depending on how you approached your tokenization. But once you choose your tokenization, you're done, because all the model knows is 42, 53, 932. And if you change the words that are associated with those, or the tokens that are associated with, then you lose all meaning. So once you choose your tokenization scheme and you begin training, you're stuck with it.
So just when it comes to like image, like I liked how the paper at least briefly touched on like images, but how you could kind of represent images by, in different ways. And it just briefly talked about it. But when you have a concept of a token, when you're talking about an image, like for example, if you're trying to find something in an image, like you want to, a cat is the example that they use a lot, like on the internet, but let's say you're looking at like a aerial photo and you want to find, cars, Yeah. And is the token going to be like a car? Or is it going to, I guess, like the card pixels for the car? I guess that would be an example maybe of the token.
So no, so it
gets really complicated. Maybe.
Think stupider.
Okay.
Right. So we get away with really silly things with tokenization because the model is such a powerful learner. So here's how they do tokenization, at least for Vision Transformer, which was very successful. There are other types now, but this is pretty much how it's done. So what you need some representation of a part of the picture, right? And you want it to sort of make sense. So what you do is you take the upper left 16 by 16.
Right.
That's my first token. The next 16 by 16, that's my next token. And really, I'm just taking the RGB values. And that I'm just using those directly. Go over 16 more, that's my next one. Next one, next one, next one. So again, just like WES, what does that mean?
Right.
Well, what is, gray, because what is this? This looks like gray, lighter gray. Doesn't mean anything. But as the model begins to learn and it uses that attention, remember, it's going to be taking those patches from all over the image, right?
Right.
And if you have a patch that looks like this, which is like, could very well be like glasses on a face. So that means, what is the most likely thing to be over here? The other side of the glasses. So it's just learning the sequences over time. So even though it's innately very, very local, it actually learns globally much faster because it's actually doing attention over all the patches all at once. And so it's attending to the entire image. And so it works differently from convolutional neural nets, which tend to be more local. It's a more global view of the entire image all at once.
Okay. All right.
And these are, the success of these models led to some hard lessons and some hard truths. Think about all the work that has gone into how to represent language, how to code it, you know, grammar, augmented grammars, you know, work of decades trying to figure out how to augment text and so it could be learned, right? Structuring it for the computer. Same thing with images. You know, certainly early in my PhD career, I was doing work with similarity in images and, you know, geoms and different types of features and feature spaces that you create to capture what's going on. And it turns out the answer is, it matters very little. What matters more is that you have a powerful learner. Other questions?
Hi,
Amy.
Jesse. I have a question that I'm hoping to ask related to something about the probability distributions.
Yes.
So when both the encoder and the decoder updates their hidden state, you mentioned earlier that they update based on time steps and they combine information from the current vectors and then these hidden states are updated. So does this updating process involve any probability distributions? So in other words, if the same input was given, do they learn and output the same results, or do they give us different output based on some probability distributions?
So let me, so the context that goes in all at once. So we do positional encoding, but it's not really just processing the context one token at a time. All the context goes in. So you can think of that as a prior. So all that goes in, then that entire context moves through this all at once. So all of the processing for a token, you know, if you take a look at with the math that we're looking at before, it's we talk about it one at a time, but really what's happening is that it's doing matrix multiplies. With this multi-head attention, it's doing matrix multiplies. With this feed forward network, it's doing it all at once. It's taking all the embedding vectors and moving them through. So it's true that it's processing the layers one after the other. So it's processing the layers one after the other, and that is, you know, what you see here is it's moving through these layers. So the entire engine, the entire, you know, everything that's happening there can be viewed as a probabilistic endeavor. So when we go up here and we go after that sequence modeling, that's really what's happening. Data, given, you know, your parameters, gives you that probability distribution over the next tokens. And then when you're generating text, what happens is that you then take what you generated, you put that back into the context and you process it all over again as another big block all over again, but all at once, right? So now you have n+1 tokens, and then you're generating off of that. And that's how you generate text, one after the other. Are probabilities explicitly in there? No. But one very valuable way of viewing this entire endeavor is from a Bayesian's perspective. And it turns out that these models are very, very good at doing very fast Bayesian work for you. So depending on how you define your problem, using a custom transformer model can work 5,000 times faster than solving that same problem using MCMC methods. Does that answer your question, Amy?
Yeah, this is extremely helpful. So Jesse, do you have any maybe related papers in terms of the MCMC process that connects with the transformer concept and the architecture?
Yes, I do. And if you'll drop me an email just to remind me, I think it's yes, I can give you sort of the original paper that was like a year and a half ago now, maybe. And I would imagine there's going to be stuff that is after that as well now.
That'd be really helpful. Thank you so much.
Absolutely. Raymond.
Are there times where actually using pseudocode would be practically more beneficial than using code?
Oh yeah, I mean, absolutely. I mean, if you take a look at that trick that we did down here, where we were flipping between the two, this is like thousands of lines of code, right? There'd be no way you could see that these are almost exactly the same.
Yeah.
Unless it's pseudocode. And the cool thing is you can absolutely code a full GPT from this. It's all specified here. You don't need all the extra code with, let me define the class, let me go ahead and, nope, don't need it.
My experience with pseudocode runs until about SVC, SVM as part of a course that ran through neural nets.
Yep.
So I was curious about that. Something, just a brief mention that I felt might help for context. I do web GTP4 iterations, ask you or whomever questions for better contextual understanding, feed the improved quality back through one or more additional sets of GTP4 iterations. That's basically how I do all of my learning.
Yeah.
So that way I wanted to mention that so you had maybe a better ballpark for, what I'm asking you, hey, please give me a really great GTP4 prompt, basically, when I ask questions.
That's it.
All right. Well, thank you for your time. You have a great day.
Absolutely. You too. Excellent. Other questions? Then I'll make another comment. I'm really serious that that this part of the paper right here, where we talk about sequence modeling. This is a great way to think about, and if you can have this always in mind, that this is at the core of what's happening, it helps so many other things make sense. Like there's a question about daydreaming, but more often you hear about hallucination. It's like all of a sudden the models go insane and they're hallucinating. It's like, well, what are you doing here? You're doing sequence modeling. You're generating sequences. That's what generative model AI models are doing. And it is trained to come up with most probable tokens. So is it hallucinating? It's doing exactly what you trained it to do. So if you ask it to cite papers for you, and it does not have access to the web, you ask it to cite papers for you, then what does it have to rely on? It only has its feed-forward networks. Only has so many of them, even if it has billions of parameters. It cannot memorize everything on the internet. There are a lot more tokens than just a billion tokens in the internet. There are trillions of tokens on the internet. So it gets the gist. So what is a likely response if you're asking for something around protein synthesis? Well, and you want articles on it. Well, it's likely that it might appear in Nature. Okay, it's likely it might have a title like this. It's likely that it might have this author because this author has appeared on other papers where they talked about protein synthesis. So that's likely. And if you remember, that's the task. So yes, it will generate for you. Is it a good idea to ask Google-like questions against an unaugmented model? It's a terrible idea because it will generate likely answers. So how do you get around it? Again, come back to here. This p hat x is defined as the p hat theta of all the following. Well, you don't get to change the thetas anymore. They're fixed. Learning is done. But maybe you can change the x. And that's where the idea comes from. come up with a better, it's like this, like come with a better prior, come up with a better description, do, you know, do prompt engineering, or add more context to it. Maybe add an automated system that will do a semantic search, or go to Wolfram Alpha and put a whole bunch of information into that prompt about plants that are toxic to animals. Now, all of a sudden, it's going to do a much better job. Because why? Because that probability has shifted now. Name 10 plants that are toxic. Okay. Name 10 plants that are toxic. Here are a list of 20 plants that are toxic. Well, now I can do a much better job, right? Because all of that information is in there that sets the context. The information is in the model, but it's a matter of narrowing it down. And that's what the context does until it can give you a good answer. Other questions?
Jesse, so just related to what you have just said, I'm wondering, maybe there are some researchers who are interested in creating a transformer or a generative model for younger children. And so they restricted their training data sets to just available for younger children and protect them from other information. So in terms of restricting that X, are there other ways instead of prompt engineering that we are just restraining the size of the training data set so that it could not use any reinforcement learning to generate new hallucinating citations?
That is difficult because of the very nature, because look at that again, p hat theta, it's all probabilistic. So it's never going to be the case where it's going to be exactly right. It's doing it at the token level, right? So even if you have simplified, because we tried that's been tried. Meta, formerly Facebook, had a model that they had very high hopes around, where it was only trained on scientific information. So, and their thinking was maybe part of the problem is kind of what you're thinking, Amy, right? It's kind of like, well, you have also, who knows what's gone into these, conspiracy theorists. It certainly has been learned on vaccines are dangerous and, cause hair loss. And it's like, all sorts of stuff. So what they did was they trained a model only on scientific papers that were published, right? No, still have the problem because, again, p hat of X, right? It's like, yeah, you change the thetas a bit, but it still is probabilistic. It's only choosing the most probable answers. So how can you fix that? Well, one way, again, modifying the X. Remember, it is producing the probabilities. Maybe what we can have is an entirely different model, which goes, and maybe have an encoder model that is extractive question answering. So it generated an answer for you. Now you go and maybe you can do a semantic search against the known literature and saying, do you see this anywhere? Do you see anything like this anywhere? And if it's like, there's nothing that matches this, then you can give the answer. You can say, I'm not able to cite where this appeared. I have low confidence. There are many different ways that you can sort of do this, but it's all around mitigation. Why? Because the heart of this, it's not something which has a technical fix, because p hat theta. Great. Other questions? All right. Well, folks, and I'm going to go and close up. I'm going to stick around for a little bit more in case anybody has questions, but otherwise, we'll see you tomorrow for our first session on LangChain.
Thank you so much. Thank you.
Absolutely. You're very welcome, Amy. Did another question come to mind?
Well, I guess I have most of my experience with AI has been like more on the convolutional networking side of things, and where we would go in and we would take like labeled pictures of cars or planes, and then we would go through a process to identify those in aerial photos, satellite photos, and that's kind of how we've done things. And it takes a lot of training data, and there's a lot of subtleties to it. Anytime you're using a different camera, different satellite, different airplane, different airspeed, different environmental conditions, different weather, different times of the year with different types of leaves on the trees or no leaves on the tree. So really problematical, for a lot of things. And so, trying to like look for lessons learned from this, tremendous advances that have been going on right now with like ChatGPT and these other generative models. This is what I'm trying to like, that's sort of the lens with which I'm looking through this, and trying to understand a little bit more deeply, what we can do to really improve that class success rate.
Right. So,
well, not really a question, I guess. That wasn't really
exactly. No, but you've touched on something that is really pretty interesting, and that is this is a total shift from how we solved problems in the past. One of the best examples of this is, so for example, robotics, right? So robotics, the whole problem with embodied cognition, this has been around for decades now. How do you allow a robot to problem solve around the world, right? It's kind of like, yes, you can move around, you can stay upright, you can perturb the movement, it can maybe move over things, but that's a doorknob over there. What do you do with a doorknob? Oh, and this one isn't round, by the way. This one's kind of like long. What do you do? And what is it good, And we were never able to get there, right? Well, natural language. So you have a large language model which knows the world from the viewpoint of what's been written about the world and maybe images about the world as well. And then so long as you have something which is language driven for the robot, which you can do, transformers are general purpose learners. So, hey, you want to have a multimodal model of which some of the tokens are robotic controls? Sure, go ahead. Now, the problem of, I would like to go through the door. All right, now it's going to generate the next most likely sequences, which could involve turning the doorknob. Right. Now it turns it into a multimodal problem. And we've entirely sidestepped the question of what is the proper representation? And because the answer is, we can't decide. We can't know, but it can be learned. I find it, so my PhD is in cognitive psychology and cognitive science. I did a lot of work in mathematical psychology, did a lot of work in representations, and I find it very humbling that those matter not very much at all. What matters more is to allow the model itself to learn what is the most useful representation.
Okay. I mean, we've also, sometimes it's not about like identifying things too. It's about like identifying where the changes. I mean, one of the models that we developed, or one of the techniques we developed, was like, it's too hard to identify some of these things, but and really what we want to know is, are things changing in a way that matter, in the environment? So for example, like, we don't really care that it's like a windy day and you can see the waves on the water, when you take a picture from an aerial photo. What we care about is the fact that, the fuel tanks are a lot lower, or, or the big ship in the harbor is gone, like that's the stuff that we care about. And how do we, statistics is a way to go about it, but you don't want to overthink it too. And then there's all these questions about like the sensor parameters and all this metadata.
Yes.
And how do you, you have like chips of images like you talked about, and that's exactly kind of how we would go about it. We'd have like a chip of what the thing looks like, but
Yeah. Think about this. So think about self-supervised learning, right? Oh, and Adam, can you hang around for a moment? Is that okay? Great. So think about self-supervised learning. So here's, we are working with Karen Johnny on gravity wave data, right? So the way that this has been approached is not dissimilar to what you're talking about right now currently, which is you have Einstein equations, which you can compute. They're very expensive to compute. And what you look for is in the presence of all this noise, do you see something that looks like two black holes colliding of these particular mass? And you look, and it's almost like, okay, do you see something that matches that pattern? If so, my God, you just made another discovery. It's huge, right? The transformer way of thinking about this and the self-supervised way of thinking about this is it is all signal. It doesn't matter if this little buzz that you have here, because these are waveforms and you can play them as sound, this little buzz right here is what you get in the 11th hour of this transformer, of this piece of equipment working, because it overheats a little bit and then cools down. That's signal. Then on Tuesdays around 8 o'clock, you get a rumble for this detector in Washington State, but not in the one in Louisiana. That would be the Tuesday garbage truck. You know, right? It's kind of like, these are all signals. Through self-supervised learning, it learns to fill in the missing parts. So it represents, it doesn't know what a garbage truck is, but it represents the garbage truck as a transient signal that occurs at a particular time of the day of the week, except for holidays, you know, and sometimes is running late, right? And that's what it looks like. You don't know what it is, but it represents it at these different levels. So it doesn't know what a garbage truck is or what heating is or what black hole collisions are, but it represents them all. And black hole collisions sort of tend to be kind of close to each other because they all look similar. They look different from garbage trucks. They occur across detectors. So instead of running the Einstein equations and looking for that particular pattern, you can say anything that looks like this, pay no attention to. It's garbage truck. Pay no attention to these things. That's an earthquake. These things are interesting. Do you see anything else that looks like this? Mm-hmm. Sure. Have a whole bunch of those. Mm-hmm. And so the idea is that you allow it to learn all of that. I didn't do any labeling. This is self-supervised. This is unlabeled. Same thing with the learning of the languages. I didn't tell it that ships at a distance have every man's wish on blank. I didn't teach it objects of prepositions or style of writing or semantics. I let it learn all of that on its own. Similarly, with images, you could let it learn all on its own. If you have something which is white but blue here, and then it's white and blue here, oh, that's choppy water. All right. It doesn't know what choppy water is, but it knows that it occurs here, and it knows that you're really not interested in it, you know, and it can label all the choppy water. Once it's learned, because it represents it the same. Why? Because choppy water here means choppy water here.
Right. Okay.
It's very different. It's very different.
Yeah, yeah. And I think especially when you get into, you know, talking about like the signal, you know, a lot of the work for doing this is beginning to be done with like synthetic aperture radar, for example, right? So you're not really looking at a picture, you're looking at a representation of, you know, data. And
you can learn wherever you want to along there, right? You can learn on raw, you can learn on, and that's the other message is that you can learn on whatever level of representation you want to. Let me take Adam's question real quick. Adam.
Great, thank you. So I wonder if you could help me make the connection between the attention example that you gave, time flies like an arrow.
Yes.
Kind of getting the idea, the meaning of soar, fly as in soar, not the insect. Can you help me see how the matrix multiplication in the pseudocode accomplishes that? I'm having trouble kind of thinking of what a vector in that attentional space represents.
Okay, so can you rephrase that just a little bit?
Yeah, sure. So how does the math accomplish what what you did very clearly, showing the
oh yes, got it.
showing
Yeah, okay.
the short vector implying soar
Okay.
in that sense.
Yes. So we didn't really talk about training, right? And you're picking up on the fact that I had a bunch of IOUs that I absolutely am not going to be able to honor in the 2 hours. But really what it comes down to, is it predictive of what the next token is? That's it. Is it predictive of what that next token is? And the answer is, I tend to answer the question that fill in that missing word better when I put under this situation, when I put wait here instead of here. So in that case, if how do I know? Let's see, is that the right one? Google Chrome, yeah, I think that's the right one. And share. Okay, so back up here to this example where we were doing the weighting. How do I know to average arrow and time? Well, because in other sentences that were similar to this, I emphasize words that were similar to those over a long period of time. So that's why you need to have massive amounts of training. This is not just, just a few passes. This can be trillions of tokens that you're training on. And by tokens, I mean, that sort of gives you an idea of like the mass of the words that you have. Trillions, billions, millions at a minimum, millions at a bare minimum, billions for some well-performing models. We're finding trillions is even better, where you are training and the task is very simple. Guess the missing word. And over that, it learns about language structure, word similarity, attentional weighting, how to actually project down for even KQV, those linear, that's learned. It's more useful if you have that much of a bias versus that much of a bias. We allow it to learn however it wants to learn based on that. So it learns, hey, these two words in this situation are similar and need to be weighted in this way.
So is there a vector in the attentional space that would represent soars, and that projection, that matrix multiplication, is taking flies in this sentence and projecting it onto this concept of soars, but it's not exactly soars, it's just something similar.
Yeah. See, the tricky thing is you only get to, attention only works on tokens that are in your context.
I see.
That's right.
Yeah. Right.
So that's why context length is really important. That's why context is really important. Could this have done a better job if you used the word soars someplace? Absolutely. Time soars like an arrow would have been so much better, so much easier. But it can do it, but only with the words that are in context. So, but you remember that it has the different layers, right? So it's not just one shot and you're done. It's like, okay, I'm going to do my attentional mechanism, then I'm going to feed it through my feed-forward network, which I'm going to say, here are the concepts that I'm starting with. Now remap them, and so I have new concepts that are related. So it may very well in the feed-forward network say, hey, flies, this is closer to soars. I'm going to give you something that's much closer to soars now than to flies. I'm still going to have 20 embeddings. I'm going to have 20 vectors, but now one of them is very close to soars. And then I'm going to do it again. And, can do it a few times, maybe 6 times. You don't tend to have like hundreds of layers, but, a few times.
Yeah. Okay, great. Thank you.
Absolutely. Other questions? All right, folks, and I'm going to close it up. Thank you all very much for your great questions. And look forward to seeing you tomorrow, where we're going to be learning more about LangChain. See ya.